Hello, student. Welcome back to this our topic of fiber optics. So, in the last session, I was discussing about this dispersion in the optical fibers. So, I discussed the dispersion phenomenon in the step index multimode fiber in the last session. So, now I am discussing this dispersion effect or phenomenon in the graded index fiber. So as I have explained in my earlier sessions, graded index fiber means that is the optical fiber in which the refractive index of the core is gradually changing as you are moving from the optic axis to the edge, means the interface of the core and cladding. Such a fiber is called as the graded index fiber. So in a graded index fiber, light rays travel at different speeds in different parts of the fiber because the refractive index varies throughout the fiber. So that's the reason the refractive index is not constant throughout the fiber, throughout the core of the optical fiber. But the refractive index is constant in the cladding, but it is not constant in the core. So near the outer edge here, outer edge in the sense, it is the interface of core and cladding. So near the outer edge, the refractive index is lower. Thus, rays near the outer edge travel faster than the rays in the center of the core, because we know that the relation between the velocity of light and the refractive index is V is equal to C by N. Here, this C is the velocity of light and N is the refractive index of the medium. So this velocity is inversely proportional to the refractive index of the medium. So because of that reason, the rays near the outer edge travel faster than the rays in the center of the core. Because of this, all the rays arrive at the end of the fiber at approximately the same time. In effect, light rays in these fibers are continuously refocused along the axis as they travel down the fiber. This leads to small pulse dispersion because during the refocusing effect, the convergence of all the rays at one point doesn't take place. So because of that reason, the pulse is dispersed, means it becomes broadened. The pulse dispersion in this case is given by, it is delta tau is equal to N2 into L upon, sorry, just a minute. Delta tau is equal to N2 into L upon 2C into del square. So this result I am not going to derive here. This is given directly for this dispersion in a graded index fiber. So dispersion due to material itself. So here the dispersion takes place because the refractive index is changing in this case. But here the dispersion takes place because of material. Even though we consider a laser source as a monochromatic one, it is not so really. The spectral output of a typical laser source is shown in the figure. So you can look at this diagram. So we say that generally the laser is a monochromatic source. Monochromatic means only one wavelength. It is having single wavelength, but it's not true. The actual output, power output of the laser is shown here. You can see that this is the central wavelength. 1.300 micrometer is the central wavelength. On either side of this central wavelength, the wavelengths are spread. You can see here. So the output of the laser source is having the wavelength which spreads from 1.298 to 1.302 micrometer. So this is the one problem, and because of this slight dispersion of the light signal takes place inside the optical fiber. So it is clear that on either sides of the center wavelength, which is 1.3 micrometer, some other wavelengths are also present. Thus, the laser source is said to have a finite spectral width. So because of this reason, some dispersion takes place. And the refractive index of optical materials is a function of a wavelength, as I told earlier. And the different wavelengths components of the laser source will propagate at different speeds along the fiber. So the different rays, we can say that the different rays of the laser source are propagating at different speeds because the refractive index is changing. The short wavelength components travel slower than long wavelength components, eventually causing the light pulse to broaden. This type of dispersion is known as material dispersion, or often called the chromatic dispersion. And now, as in the case of what is that multimode fiber, we have calculated the time delay for the multimode fiber. So here I am going to derive the time delay due to this material dispersion. Consider a plane wave propagating in fiber core. So the plane wave is described by the function psi is equal to e raised to I into kx minus omega t. So this is the plane wave, as you know, and this is the angular velocity, t is the time, and k is the wave vector or propagation vector, and x is the displacement. So where the wave number k is defined by k is equal to 2 pi by lambda. This we know. This k is most or often referred as the wave number or propagation vector. It's given by 2 pi by lambda. And this can be written as omega was c into n. So because omega is equal to 2 pi f, so 2 pi is there, you are multiplying and dividing by f here. So the here 2 pi f becomes, so that is omega, and f lambda is c. So in this way, you can rewrite this equation in this form, omega by c into n, where this n is the refractive index. And the group velocity Vg is defined by the equation Vg is equal to d omega by dk. So this is the standard definition for group velocity. What is group velocity? Group velocity is the average velocity of the group of waves which are traveling in one direction. Why this concept of group velocity comes here? Because even though we are taking laser as a source, it is not having the single wavelength exactly. It is having a spectral width. That means wavelength spread is there. So because of that reason, the different waves in the core propagate with slightly different velocity. So we can say that there are a group of waves propagating inside the core. So the average velocity of this group of waves propagating inside the core is called as the group velocity, and by definition always it is Vg is equal to d omega by dk, where this omega is the angular frequency and k is the wave number. Reverse this equation, it becomes 1 by Vg is equal to dk by d omega. So this is equal to d by d omega of k, and this k from equation 2, it is omega by c into n. Now you differentiate this equation with respect to d omega, and this is equal to, so here two things are there. So you have to apply the product rule of differentiation. So it becomes n by c into differentiation of this omega with respect to omega is 1. So it is only n by c plus. And now you are keeping omega by c as it is, and you are differentiating this n refractive index, because here c is the velocity of light, and that is also taken as a constant. So you are differentiating this n refractive index with respect to this omega. So this becomes d omega by dw, or d omega, dn by d omega. And c is common here. You can take it out. It becomes 1 by c into remaining in the bracket is n plus omega into dn by d omega. So this is the equation 4. Next, let this lambda not be the free space wavelength defined by lambda naught is equal to 2 phi c by omega. Again, this is just making use of the standard relation between wavelength, frequency, and angular frequency of a wave. So 2 phi f is equal to omega, and f is written f is the linear frequency that can be written in terms of c and this velocity of light and wavelength. So you can work out. So this lambda naught can be written as 2 pi c by omega. This is the free space wavelength. Free space wavelength means it is the wavelength of the light when it is moving in the free space, or it is also called as a vacuum. Differentiating this lambda naught with respect to omega, we get so d lambda naught by d omega is equal to 2 pi c. 2 pi c is a common. You are differentiating only 1 by omega, and so it is minus 2 pi c divided by omega square, because the differentiation of 1 by omega is minus 1 by omega square. Now this dn by d omega can be written as dn by d lambda naught into d lambda naught by d omega by chain rule. And this is equal to this, you keep as it is dn by d lambda naught, and d lambda naught by d omega, its value is available from equation 5. So you substitute this here in place of d lambda naught by d omega. So you got the equation 6. Next, substituting dn by d omega from 6 into equation 3. So we have to substitute this equation 6 into 3. Equation 3 is here. It is 1 by Vg is equal to 1 by C into n plus omega into dn by d omega. So here dn by d omega is there. So for that we have to substitute from this equation 6, dn by d omega is this much. So you are substituting that quantity in equation 3. So this equation 3, 1 by Vg becomes it is 1 by C into n plus omega into dn by d omega was there. Its complete value is substituted here. So actually here this is written first and then it is written next, and this should be minus, slight mistake is there. That is corrected here. And 1 omega get cancels here, and you are left with 2 by C by omega. So 2 by C by omega from equation 4, here equation 4 is there, it is lambda naught. So that is substituted, this thing is substituted as lambda naught after cancelling this 1 omega with this 1 omega. And this is, you are writing as it is dn by d lambda naught. So this I have corrected, minus sign was left here, so it is written. It is value of 1 by Vg is equal to 1 by C into the bracket n minus lambda naught dn by d naught. The time taken by a pulse to traverse a length capital L of the fiber is given by t tau. Time tau is equal to L by Vg. It is a normal definition of velocity. Velocity is equal to length divided by time. So you are writing for time. So it is time is equal to length divided by velocity. And this 1 by Vg value you are substituting from equation 7. So after substituting, it becomes L by C into the bracket n minus lambda naught into dn by d lambda naught. So this is the equation 8. As tau depends on lambda naught, so lambda naught, it depends on lambda naught, it is clear that different wavelengths take different time for propagating a certain length of the fiber. If the source is characterized by a spectral width delta lambda naught, then each wavelength component will take different amount of time. Then pulse dispersion delta tau due to material dispersion is given by delta tau is equal to, it is d tau by d lambda into del lambda naught. So here it is d tau by d lambda naught into delta naught was there. So you are substituting the value of tau from equation 8. From equation 8, tau is equal to L by C into n minus lambda naught into dn by d lambda naught is there. So that you are substituting here into delta naught is there, it is missed, and now you are differentiating this with respect to lambda naught. So the first term, which is independent of lambda naught, goes to 0. this term as the differentiation rule, and next only the second term is left. So second term you are writing as this lambda naught into L upon C, lambda naught into L upon C, this negative sign is also there. And this dn by d lambda naught becomes dn square n by d lambda naught square into delta naught. Here also delta naught is there. Delta lambda naught here is also here. So delta lambda naught is there. So therefore, delta 2 is equal to this much, that is minus lambda naught L upon C into d square n by d lambda naught square into delta lambda naught. So from the above equation, it is seen that the amount of pulse broadening is directly proportional to the spectral width of the optical source. So here the optical source is generally the laser source. Even though we said that the laser source is a monochromatic source, but actually it is having some spectral width. So because of that spectral width of the optical source, so this time dilation is there. So this time dilation is there. So because of this time dilation, there is a broadening of the signal at the end of the or at the output of the or at the other side of the optical fiber. So this is the expression for time delay due to materials dispersion and also due to the optical source. And waveguide dispersion, another type of dispersion is there. It is called as the waveguide dispersion. So waveguide dispersion arises from the guiding properties of the fiber. The group velocities of modes depend on the wavelength. I explained what is this group velocities. So group velocities is the common velocity of the group of waves, and that depends upon the wavelength and the mode of propagation. Hence, the refractive index of any mode varies with the wavelength. It is equivalent to the angle between the ray and the fiber axis varying with the wavelength, which subsequently leads to a variation in the transmission times for the rays, and hence a dispersion takes place. So waveguide dispersion is generally small in MMF. MMF means the multimode fiber, but it is important in SMF. SMF means the step mold fiber or the single mode fiber. So the total dispersion is now given by the total dispersion introduced by an optical fiber is given by the root mean square value of all the three dispersions. Thus, the total dispersion is root mean square values of all the dispersions. So it is root is there under the root squares. So delta 2 square, that is due to intermodal dispersion. Delta 2 square, that is due to the material dispersion due to material, and delta 2 square due to the waveguide. So this gives the net dispersion produced by an optical fiber when the light rays are propagating inside the core. So this is This is about dispersion. It's all about dispersion. And I will explain this one more phenomenon, small thing. The maximum bit rate. What is this maximum bit rate? The maximum bit rate in fiber optic communication system is defined as the reciprocal of time delay. That is a maximum bit rate is equal to 1 by delta tau. So this delta tau is the time delay. So the reciprocal of time delay is called as the maximum bit rate. For example, in a fiber optic communication system, if the time delay, that is the time lapse between two successive pulses is, for example, delta tau is equal to 10 to the power minus 8 second. Then the maximum bit rate is about 10 to the power plus 8 second. So therefore, 10 to the power plus 10 to the power plus 8 pulses are sent per second in such a communication system. To achieve this, each pulse should be of 1 nanosecond. To achieve this, each pulse should be of 1 nanosecond. So that means each pulse second should be of 1 nanosecond. Such a small pulse we will have to send inside the optical fiber for the fruitful propagation of the wave. So this is about a maximum bit rate. So this maximum bit rate in fiber optic communication system is defined as the reciprocal of time delay. That is maximum bit rate is equal to 1 divided by time delay. So this decides the size of the pulse. What is the importance of this bit rate? Is that what is the proper size of the pulse which can be sent into the optical fiber is decided by this maximum bit rate. So in the next session, I am going to explain about this optical fiber communication. And today's session is this much. Thank you for listening.